the man who changed mathematics forever, the father of algebra, Al-Khwarizmi, 780 to 850 CE. Born in Khwarezm, modern-day Uzbekistan, Al-Khwarizmi became a leading scholar at the House of Wisdom in Baghdad. Muhammad ibn Musa Al-Khwarizmi stands among the most influential scholars of the early medieval world. Active in the first half of the 9th century during the Abbasid Caliphate's Golden Age, he produced foundational works in mathematics, astronomy, geography, and computation. His systematic, algorithmic approach to calculation and his textbook treatment of solving equations transformed scattered arithmetic and problem-solving techniques into an organized discipline, algebra. Over centuries his ideas spread from Baghdad into the medieval Islamic world and then into Europe, and two English words central to modern science, algebra and algorithm, owe their etymological roots to his work and name. This essay explains his life and context, summarizes his major works, mathematics, astronomy, geography, describes his methods and innovations, especially in algebra and arithmetic, traces his transmission into Europe, and evaluates his long-term legacy for mathematics and computing. Historical context and biography. Precise biographical details for many medieval scholars are often sparse, and Al-Khwarizmi is no exception. He is generally identified as Muhammad ibn Musa Al-Khwarizmi, the name meaning, Muhammad, son of Musa, the Khwarezmian, indicating origin from the region of Khwarezm, in present-day Uzbekistan, Turkmenistan region. Most scholars place his floruit around circa 780 c. 850 CE and situate his activity in Baghdad where he is associated with the intellectual center known as the House of Wisdom, Beit al-Hikmah. There he worked among scholars translating, editing, and expanding mathematical, astronomical, and geographical texts from Greek, Persian, and Indian sources into Arabic. The environment of the Abbasid capital at the time was uniquely supportive of scholarship. The Caliphal court patronized translations and original research, facilitating scholars access to earlier works and to astronomical and mathematical data. Al-Khwarizmi's contributions also reflect synthesis. He drew on Indian arithmetic, the positional decimal system, Hellenistic mathematical reasoning, and Persian, Babylonian astronomical tables. The result was not merely compilation. He reorganized material into clear, pedagogical forms and introduced algorithms and solution procedures that allowed others, both practitioners and later scholars, to use mathematics reliably. Major works. An overview. Al-Khwarizmi produced several works. The most famous and widely influential include Al-Kitab al-Mukhtasar fi Hisab al-Jab wal-Muqabala, the compendious book on calculation by completion and balancing, a textbook that systematically treats the solution of linear and quadratic equations, establishing algebra as a distinct discipline. On the calculation with Hindu numerals, often referenced in Latin translation as Algorithmi de Numero Indorum, a treatise that presented the Hindu-Arabic decimal positional numeral system and arithmetic algorithms, significantly accelerating its adoption in the Islamic world and later Europe. The Latinized form of his name, Algorithmi, gave rise to the modern term algorithm. Zij al-Sindind, astronomical tables, and other astronomical and geographical treatises. Here he updated and systematized earlier material, including Ptolemy, and provided coordinates and corrections used by later geographers and astronomers. Together these works show both a practical bent, giving merchants, surveyors, and astronomers usable rules, and a pedagogical purpose, to teach methods clearly, in words and worked examples rather than in terse formulae or isolated tricks. Algebra in Al-Khwarizmi's book, Method and Content. Al-Khwarizmi's Al-Kitab al-Mukhtasar is properly regarded as the first major treatise to present algebra as an autonomous discipline. Instead of simply collecting problem types or producing sporadic solutions, he classified equation types, using geometric language and rhetorical descriptions rather than algebraic symbols, focusing on positive quantities and positive solutions as was the arithmetic convention of his time. Introduced al-Jab, literally, restoration, or completion, the operation that moves subtracted terms to the other side of an equation so that no negative quantities appear, and al-Muqabala, balancing, the subtraction of equal terms from both sides so like terms cancel. These operations are the procedural heart of what we now see as elementary algebraic manipulation. Presented step-by-step solution procedures for linear and quadratic problems and gave geometric arguments for certain results, reflecting the long-standing Greek geometric tradition. Organized worked examples in a didactic sequence so that learners could master both technique and conceptual understanding. In modern notation, his classification reduces to a set of basic equation types, for example, ax squared equals bx, ax squared plus bx equals c, etc. And he provides methods to reduce everyday numerical problems to these forms and solve them systematically. This organization, moving from problem types to systematic solution techniques, is why historians call him a foundational figure for algebra and why the discipline's name in many languages derives from the title of his book. The Arithmetic Treatise and the Spread of Hindu-Arabic Numerals. Al-Khwarizmi's treatise on calculation with Hindu numerals played a pivotal role in popularizing the positional decimal system in the Islamic world. That system, using digits 0 to 9 with place value, offered a far more efficient and flexible framework for calculation than earlier non-positional systems. The treatise was translated into Latin in the 12th century, a work often referred to in Latin as Algorithmi de Numero Indorum. Medieval European mathematicians and merchants who read these Latin versions encountered, via Al-Khwarizmi's exposition, robust procedures for addition, subtraction, multiplication, division, and extraction of roots in the decimal positional system, practical algorithms which made computation faster and error-resistant. The Latinization of his name in the context of these arithmetic algorithms led to the adoption of the word algorithm in European languages to mean a fixed, mechanical procedure for calculation or problem solving. Because of these translations and the practical utility of the system, Europe gradually abandoned Roman numerals for many commercial and scientific tasks, a transition fundamental to later developments in bookkeeping, astronomy, engineering, and later, computing. Astronomy and geography, practical science and data refinement. Al-Khwarizmi also wrote on astronomical tables and geography. In his astronomical works, often called Zij, he compiled tables and procedures useful for calculating planetary positions and for calendrical and astrometric tasks. In geography, he produced a work, often translated as The Image of the Earth or similar titles, that revised and extended Ptolemaic coordinates for cities and landmarks, correcting certain errors and improving regional maps. These projects reflected a scientific culture that combined inherited Hellenistic models, Persian astronomical traditions, and data from observations in the Islamic world. While his algebraic treatise is pedagogical, his astronomical and geographic works are more data-driven. They are practical references for scholars doing computations in astronomy, navigation, and cartography. His systematic approach to astronomical tables influenced later Islamic astronomers and cartographers. His geographical revisions were used as references for centuries. This rhetorical style is not a weakness. It was the norm of his era and it served educational purposes. Students could follow methods in a stepwise fashion, and the lack of symbolic shorthand did not prevent the introduction of structural concepts like classification of equation types, systematic solution methods, and the idea of reduction and balancing. Over later centuries, symbolic notation developed, first in the Islamic world, later in Europe, and the symbolic algebra we use now made manipulation more compact and general. But the structural core, classifying and solving equations, is already present in Al-Khwarizmi's work. Transmission into Europe and long-term impact. Al-Khwarizmi's works were translated into Latin between the 11th and 12th centuries during a period when European scholars sought Arabic scientific and philosophical texts from Spain and Sicily. The Latin translations, both of his arithmetic on Hindu numerals and of extracts from his algebraic treatise, were instrumental in transforming European mathematics. Medieval European scholars and merchants gradually adopted the Hindu-Arabic numeral system and algorithmic arithmetic. Algebra evolved further in the hands of later mathematicians, from Fibonacci to Cardano and beyond, but always built on the basic structural approaches that Al-Khwarizmi formalized. The names, algebra, from al-jab, and algorithm, from the Latinized algorithmi, testify to the deep imprint of his work in the lexicon of science. More than etymology, his broader influence lies in establishing algebra as a field for solving general classes of problems, introducing systematic procedures, and promoting reproducible calculation. Modern perspectives. Why Al-Khwarizmi still matters. From a modern viewpoint, there are several reasons Al-Khwarizmi's work matters. Founding pedagogical structure. He provided a textbook model, systematic classification of problems with explicit solution methods, that shaped how mathematics is taught even today. Algorithmic thinking. His stepwise procedures are early expressions of algorithmic thought, breaking tasks into elementary operations, repeatable and describable rules, the conceptual ancestor of modern algorithms in computer science. Numerical infrastructure. By promoting the positional decimal system and arithmetic algorithms, he contributed directly to the practical numeric infrastructure that underlies modern science, commerce, and computing. Interdisciplinary practice. His activities in astronomy and geography alongside mathematics exemplify a medieval scientific polymath's approach, theory and data, method and observation, calculation and mapping, which prefigures later scientific synthesis. In short, Al-Khwarizmi is not merely a historical curiosity. He represents a turning point where mathematics evolved from procedural know-how into a teachable, systematic discipline whose methods could be transmitted, refined, and applied across many domains. Caveats, historiography, and scholarly nuance. While lauding Al-Khwarizmi's achievements, modern historians also emphasize nuances, attribution and sources. Some content in his writings draws on older Indian, Persian, or Greek sources. Al-Khwarizmi synthesized and made these materials more systematic and accessible. There is scholarly discussion about the extent to which specific methods originated with him versus being reworkings of previous traditions. Rhetorical versus symbolic mathematics. Because his algebra was rhetorical, it looks different from modern symbolic algebra. That can make direct comparisons misleading. Al-Khwarizmi's achievements are best appreciated in the context of his time and the educational needs he addressed. Positive quantities convention. Al-Khwarizmi and many contemporaries worked with positive coefficients and positive solutions. Negative numbers and zero as abstract algebraic objects developed later. This historical specificity should temper claims that he had the full modern conception of algebra. Instead, he established the structural basis that later mathematicians abstracted further. Acknowledging these nuances does not diminish his role, rather it situates him accurately within a chain of cumulative intellectual development. Practical examples from Al-Khwarizmi, illustrative, non-technical. To appreciate his method, consider how he would frame solving a quadratic. In words, he would reduce a given practical problem to one of a few standard types, e.g., a square and 10 roots equal 39. Then apply completion and balancing to isolate the unknown, carry out arithmetic operations, and provide the numerical root, often with a geometric justification. His examples were often concrete, problems about land areas, shares, or easements that could be translated into the algebraic templates he established. This practicality made algebra useful for merchants, surveyors, and scholars, thereby ensuring it spread quickly. Legacy in education, science, and computing. In education, the legacy is visible. Algebra is taught as a central branch of mathematics, following the same pedagogical principle of defining classes of problems and giving general procedures. In science and engineering, the positional numeral system and algorithmic thinking underpin everything from numerical analysis to large-scale computing. In computer science, while modern algorithms are far more abstract, the word and the core idea, procedural, stepwise rules for solving tasks, trace back to the methodological spirit exemplified by Al-Khwarizmi's arithmetic and problem-solving texts. Conclusion. Muhammad ibn Musa Al-Khwarizmi is rightly celebrated as a foundational figure in the development of algebra and algorithmic procedure. Working in the vibrant intellectual milieu of 9th-century Baghdad, he synthesized knowledge from diverse traditions, organized and presented it with pedagogical clarity, and offered reproducible procedures that changed how calculation and equation solving were taught and practiced. His works helped transmit the Hindu-Arabic numeral system to wider audiences, influenced medieval Europe through translations, and left an enduring imprint on mathematics and computation. Two modern terms, algebra and algorithm, are everyday reminders of his long and productive intellectual legacy.